Hello everyone, welcome to today's lecture. This is another lecture of the course on Cyber-Physical System Fundamentals, and in this lecture I'm continuing to teach Embedded Systems Fundamentals of Cyber-Physical System Design. This is the 12th lecture. This is the fourth and final lecture that corresponds to the third chapter of the companion textbook. That is the chapter on embedded system hardware. In this chapter, I have grouped the different topics according to their position in the so-called hardware in the loop. You should remember that initially we can think of starting with the physical environment. And then the first type of components that I discussed are the sensors. Then we discussed the conversion to the digital world. I talked about information processing, and we will still have to look at displays, conversion back to the analog world, actuators, and, well, not really the impact on the physical environment. Somewhere in between, and that's more or less arbitrary, I have to discuss communication, and I decided to talk about communication right now at the beginning of this lecture. So for communication, what do we have to consider? Well, for communication, we do have a lot of requirements which are resulting from the interfacing between embedded systems and the physical environment. So therefore, we have this very long list of requirements. First of all, we need to make sure that communication maintains our real-time specifications. Furthermore, we also know, due to the general properties of embedded and cyber-physical systems, that communication should be efficient. For example, it would be a very good idea not to require having distributed power supplies everywhere in a distributed system, but to try to have somehow a centralized power supply. Furthermore, like always when we consider communication, there should be an appropriate and also we definitely need to have an adequate communication delay. So if we really have a real-time requirement, then it may be necessary to guarantee a certain maximum communication delay. Also, these systems are sometimes used in a very rough environment. So therefore, we have to make sure that these systems are robust as needed by that environment. And that means that some of the cables, some of the connectors, etc., cannot be used, for example, if we think about, say, steel fabrication. Furthermore, and that's also due to the integration into the physical environment, we have to guarantee a certain fault tolerance. Faults do happen, and therefore we have to make sure that we do have appropriate techniques for handling these faults. Then these systems should be diagnosable, so in case something goes wrong, we have to be able to figure out what went wrong, and then hopefully, maybe even online, we are able to get the system back up and running. And then we have to make sure that this returning the system into full operational mode does indeed work. We have to make sure that maintenance is feasible, so should it be necessary to take the system offline for some time, there should still be some support that allows us to maintain the system. And then, resulting also from the general requirements for embedded and cyber-physical systems, we do have to guarantee that our system is secure. So if there is, for example, some communication that is supposed to be private, we have to make sure that this communication actually remains private. And also, since some of these systems are safety critical, we have to make sure that the communication doesn't violate this requirement. So we have to make sure that, for example, a dropping communication line, other problems during the communication do not cause harm to anyone. So there's a large set of requirements, and I cannot really talk about all of these because this list is so long, and there are so many techniques that can be used, so I can just provide examples here. And I'd like to start with an example that tries to improve the robustness of our communication techniques. And I'm trying to improve robustness at the electrical level. At the electrical level, we can improve robustness over a communication technique that you possibly do assume frequently by having the transition from so-called single-ended wires towards differential signaling. So in many of the cases, I guess you will be assuming that whenever you are implementing some signal by providing a certain cable across which this signal can travel, you assume that there is a common ground signal and there is one wire over which that signal can travel. Now in this scenario, we would typically have an output that is driving the cable, and we would have one or more inputs that are receiving the signal there. And it would be a possibility to indicate with a positive voltage that we are trying to communicate a logical 1, and with a voltage close to 0 that we are trying to communicate a logical 0. However, there's a problem with such electrical circuit, because if we have, for example, a very long cable over here, the signal will get attenuated, and as a result, we will not have the full voltage over here at the input, and this may lead to the question whether a certain intermediate voltage corresponds to a logical 1 or a 0. Problems like that one can be avoided with differential signaling, where each signal is encoded on 2 wires, and these 2 wires are typically twisted so that any noise gets added more or less equally to both of them. And then these 2 wires are connected to the corresponding input. And at the input, we will compute we will measure the voltage between these 2 input pins. If at the positive input we have a positive voltage with respect to the negative input, then we could consider that to be an encoding of a logical 1, for example. And if it's the other way around, we could be accepting that or considering that as an encoding of a logical 0. Now the key advantage is actually that most noise is indeed added to both wires. So if we perform this subtraction over here, we more or less remove all the noise. So that's the key advantage that we get from differential signaling. Subtraction removes most of the noise. Then furthermore, with this organization, changes of the voltage levels have no impact because we don't have to make up our mind whether some intermediate voltage reflects a logical 1 or a logical 0. Furthermore, there is a reduced importance of ground wiring. In this single-sided scenario, we could have a situation where there is a very high current flowing across this ground wire, and as a result of that, there could be a certain voltage between the 2 ends of the ground wire, and this would really interfere with the reception of the signal over there, and therefore ground wiring can be a problem there. But for differential signaling, ground wiring isn't really a problem because we just compute the difference between the voltages there on the 2 lines. Due to all these advantages, we can achieve a higher speed, which of course is very nice by itself. There are, of course, also disadvantages. The most obvious disadvantage is that we also need a negative voltage. This requires a more complicated power supply, additional lines for the power supply, etc. So that comes with an increased cost. And then furthermore, obviously, we need more wires and more connectors, which makes these connectors larger, which makes these connectors more expensive. So also that's obviously a disadvantage. But nevertheless, the advantages are very strong, and therefore differential signaling is used in many applications. It has been used even before digital communication was the de facto standard. Even analog circuits have been using differential signaling for quite some time, and that means even, for example, this microphone. over here is using differential signaling. So this is actually the connector of this microphone. For the same reason, differential signaling was used in certain versions of SCSI, an interface technique that is used between computers and, for example, hard disk. The server versions of SCSI typically use differential signaling. And also, because of these advantages, Ethernet is mostly using differential signaling, except for very early versions of Ethernet and for versions that are based on wireless LAN techniques or optical communication. So this is the well-known connector for the standard Ethernet. And for the same reason, FireWire, ISDN, USB, and the list could be extended, are all using differential signaling. So that's one technique that I provided as an example of what can be done in order to improve the robustness. Next, I'd like to look at a second example. And the second example being the need to guarantee a real-time behavior of communication. With respect to real-time behavior, we can have a look at one of the standard techniques that is used for communicating between different computers. You know that there we're using Ethernet, and for Ethernet there are different variants. The very early versions of Ethernet were based on these types of connectors, where we could connect various outputs to one wire, wire that was used as communication media. And it could happen that these different outputs were driven at more or less at the same time, and as a result, it was possible to have collisions, and these collisions had to be detected, and then a retry had to be tried for a certain maximum number of times. If that maximum number of times had been reached, the whole communication was dropped. So in this case, we require that this collision at least be detected. Due to the retries, there is obviously no guaranteed response time. So we have to look for other options, and some of the other options that we can use there are based on the idea of not trying to look for possible conflicts between communication partners at the time when we propagate the actual message, but to do this in a separate phase. And this is used, for example, for most wireless LAN techniques, and this also applies to certain standards for bus-based communication. There, before we do the actual transmission, we check which of the communication partners would like to communicate, so the communication partners can kind of raise their hands and tell the system, oh, I'd like to communicate. And then the highest among all those partners, the highest priority among all those priorities will be considered, and that will be the one that can actually then transmit the message. So in this way, we have only a very short interval during which all these partners can indicate that they would like to transmit something over the communication media, but there is no conflict during the actual transmission. There are other techniques such as token rings and token buses. With respect to buses, I would like to present one technique that is used in many buses that are designed for real-time environments. In a standard bus system, we could have a number of devices that are connected to a bus, and then the standard bus system could be priority-based. That means, based on some more or less fixed priorities, we would be deciding among competing devices which of these devices would be allowed to access the bus. So as a result, we would again have no real-time guarantees except for that device that has the highest priority, and this has already led to some problems. You might have seen cases where, for example, for very old PCI buses, you had a situation where a certain fast card had to be placed next to the graphics card or next to one end of the bus, because there it had the highest priority, and this highest priority was required for a card that needed the maximum communication bandwidth. So that is something that's not very nice for a real-time environment, and therefore we have to do something different. So this something different that can be done includes the use of so-called time division multiple access, or TDMA buses. For TDMA buses, each communication partner is assigned a fixed time slot. So for example, we can think of dividing the time into so-called frames. These frames are typically all of the same length. And then within such a frame, we do have allocated slots, or so-called slices. And during these slices, the communication partners have the exclusive right to transmit their information during that particular slice. So during such a frame, we typically have the indication that the frame is somehow starting. There is a certain frame gap which may be needed because the synchronization character is transmitted from a communication partner different than the one communicating the first slice. And then we have a sequence of slices, and then the whole process is repeated. Down here you see, again in textual form, how this is supposed to work. There is a master also for this bus. This master sends the synchronization indication. There may be some waiting time in order to allow all the different partners to realize that it's now their time to communicate. And then each so-called slave, or each communication partner, has to transmit, or is allowed to transmit during its time slot. It's not allowed to transmit during any other time slot. It can possibly leave a particular time slot empty. There exist certain variations, like for example truncating unused slots, so that in this case we are violating a little bit, or we are stepping a little bit away from this very static structure. We could think of just skipping slots that are not needed. This would not really violate our real-time constraints. We can also allow for slaves or communication partners to be allocated more than a single slot, so that in this way they get a higher bandwidth. In general, these TDMA-based buses do have a deterministic timing behavior, and they are also used, for example, in networks on chips where we have to guarantee a certain quality of service. Now, this idea of using time division multiplex is also used in a very recent standard that is proposed for the automotive domain. In the automotive domain, there is now the transition towards a communication protocol called FlexRay. FlexRay was developed by a consortium of automotive companies. Interestingly, it was specified in SDL, so this tells you that the coverage of SDL in our course is indeed very useful, because we see this in a number of examples, in a number of applications. And concerning FlexRay, we have to compare the new standard with the dominating existing standard, which is the CAN standard. CAN is the standard communication used for most cars these days. However, it is known that for CAN there are certain problems, because CAN is too slow. There are certain cases where we have difficulties guaranteeing meeting timing constraints. So therefore, it is reasonable to look at this more advanced standard for communication in cars. With this FlexRay standard, we can meet higher transfer rates. Initially, FlexRay was targeted for 10 megabits per second, but the design allows for much higher data rates. Also, compared to the CAN standard, the FlexRay standard does provide a much more improved error tolerance and much more time deterministic behavior. And it is, as can be expected from my introduction, it is using the TDMA protocol. In order to make the standard somewhat flexible, it is not just based on a very strict TDMA protocol, but there is some dynamic behavior there in the system. Therefore, each communication cycle is subdivided into a static segment that provides the guarantee for the real-time behavior, and a dynamic system that would typically be used, let's say, for multimedia data. So, this is the typical structure of a FlexRay system. In a FlexRay system, we do have different communication partners, or so-called nodes, that can be connected to up to 2 different channels. For reliability reasons, there are 2 channels available, and each of the nodes that is safety critical must be connected to both these channels. There may be some other nodes that are less safety critical and which could then be connected just to one of these channels. Now, for such a FlexRay system, there is a assigned communication time, or a so-called slot, for each of the nodes in the system. In each of these slots, exclusive bus access is provided for the corresponding partner. In this dynamic segment, we do have the possibility of using a variable length interval there in case we are transmitting, for example, say, multimedia data. Within the dynamic segment, we also have fixed priorities. We will have a certain so-called mini slot available for each of the nodes there, and during each of the mini slots, the communication partners can kind of raise their hands and tell the system, I'd like to communicate, and then they can get a corresponding amount of time there from the system. So due to this somewhat more flexible approach for the dynamic part, we will be using there the bandwidth only when it's actually needed. So down here you see this situation in this example one more time. You see that over here we are communicating the message provided by node A, and then we have information provided by B, by C, by D, and we can have this situation where to one node we have allocated more than one time slot, so that in this case this very important node might have a higher bandwidth than the other nodes. And over here we have the dynamic part, where we have the different mini slots, and these mini slots are allocated to the nodes here in the system, and during these mini slots these nodes can raise their hands and tell the system, I'd like to communicate. Now this is a somewhat more detailed view of the timing in such a FlexRay system. You see the different cycles over here, and during each of the cycles we have this static segment, which is comprised of the different slots, in this case n different slots. And then in addition we have the dynamic segment, and in the dynamic segment we have these short intervals of time during which these partners can raise their hand, and there are some cases in this example where a particular partner is actually communicating something. Then there is an optional so-called symbol interval during which we can communicate a particular symbol to check whether or not the whole system is still working. And finally, there is some network idle time. Now, with respect to the timing in these FlexRay systems, there is sometimes confusion. So therefore, I'm presenting the timing model here. For a FlexRay system, we are allowed to have different local clock speeds in the different nodes. And these clock speeds there in the different nodes, they are defining the different microticks. So for each node, we can have a different microtick depending on the frequency of the local clock. Then based on the frequency of the local clocks, we define a common interval that is to be used by all the different components, which is a multiple of the local clock frequencies. So it may happen that for each of the communicating partners, we do have to use a different multiple so that we arrive at a common so-called macro tick. The macro tick is the basic unit of time, and multiples of such a chunk of time are allocated to the different intervals that we need during this communication protocol. The slot is the amount of time which is allocated per sender in a static segment, and such a slot is one multiple of the macro tick, and this multiple can be configured depending on the particular application. Furthermore, there is the notion of so-called mini-slots. Mini-slots are the amounts of time that are allocated per sender in the dynamic segment, and again, such a mini-slot is a multiple of the amount of time that we have there for the macro tick. And finally, there is a definition of a cycle. A cycle comprises the static segment, the dynamic segment, the optional symbol window, and finally the network idle time. So that was the timing there for FlexRay. For FlexRay, we have very careful design in that we are trying to care about possible sources of unreliability, and therefore the designers of FlexRay also have tried to implement measures against so-called babbling idiots. As a result of certain errors in the different devices that are connected to these channels, there could be a situation which is very boring in a technical system. It's boring in a very similar way to the way it could be boring in a real environment, because there could be a situation where we have so-called babbling idiots. That means there will be a lot of noise that is propagated, and we can hardly do our work that we are supposed to do because of these babbling idiots. Now, FlexRay systems have an advantage in this case, because for FlexRay systems we have a so-called bus guardian which is supposed to protect the communication controller against these babbling idiots, so that this communication noise doesn't really reach the communication controller, and also, of course, it doesn't reach the microcontroller that is hosting a particular device. So in this way, we are caring about the overall reliability and dependability of the system. So that concludes the presentation of FlexRay. In general, there are many different standards for communication, and the requirements for communication really depend on where we are using the communication. In a complex system, there is a need to communicate between the sensors and the actuators and the adjacent parts of the system. In this context, we need a very small propagation delay. So propagation there should be a small fraction of a second. But fortunately, in this context, we only need to communicate small amounts of information. Then a little further away from the sensors and actuators, we have usually a little more time for this communication, but we are also communicating larger amounts of information. And for this purpose, so-called field buses have been designed. Field buses don't react as fast as these sensor and actor buses, but they are designed for larger amounts of data. So, for example, they could be based on packet processing, for example, instead of the type of processing that's used over there. And then we can proceed further and look at local area networks, wide area networks, where the delay that's allowed for the communication may be larger, but also the amount of information that is to be propagated also may be larger. And then, say, at the company level, we could allow for quite a number of seconds, but we would also transfer huge amounts of data, maybe megabytes, gigabytes, and these days possibly also terabytes. There are a lot of buses that can be used for all these purposes, and I'd like to mention a few of them. There is IEEE 488, which is a bus designed for laboratory equipment. So, for example, oscilloscope can be connected using IEEE 488. There is the CAN bus that I already mentioned. It's a bus used in many cars. But the CAN bus alone is not sufficient for cars. There is, in addition, a low-cost bus which is used for interfacing sensors and actuators in the automotive domain. There are obviously cases where CAN controllers could be too expensive and where we prefer to have a application of the LIN bus. And then there are cases where in a car we have to communicate huge amounts of data. This is not really the area for where the CAN bus is pretty strong, so therefore there is another bus standard that's available. It's the MOST bus, which is used for multimedia in the automotive domain. It could be used, for example, for providing the rear passengers with some videos. There is a bus designed for car factories called the MAP bus. Then there are buses there that are designed for smart buildings and for smart homes, like the Prof bus and the European installation bus. And in many of these cases, there have been the attempts to use Ethernet. But when people try to apply Ethernet for these cases, there is frequently the problem that timing predictability is not guaranteed by all variants of Ethernet, and also the physical robustness of the connectors, for example, is not sufficient for many of the rough environments. So therefore, things are changing there all the time, and we see a huge number of bus standards to provide the necessary means of communication. These days, obviously, there is an increased trend towards wireless communication, and again, there are many standards. I can't really present all these standards, therefore I'm just listing them on the slide. There are the wireless standards that are linked to the Ethernet standard. IEEE 802 is describing the Ethernet standard. .11 is a standard that applies to wireless communication, and for wireless communication there are again different variants using different data rates and using different frequencies and trying to increase the amount of data that can be transmitted per second. Then there are the standards that are used for communication between mobile phones and base stations, and the same standards are also used for wireless connectivity of laptops, for example, and smartphones. These include the 3G standards, 4G standards, and I think we will see more standards here. Standards for wireless phones at home also include protocol parts, protocol components that allow you to communicate data, even though I think that is less widely known. And there are other standards like Bluetooth, Zigbee, etc. Concerning the link to real-time systems, we do have in many cases a problem that the precise timing is very difficult to predict, and in many of the cases we do have to figure out whether or not we can provide any timing guarantees. Also, in the context of cyber-physical systems, the energy consumption required for communication is very important, and we will look at the energy consumption, for example, at WiMAX devices in Chapter 5.